Graphing piecewise defined functions. Sometimes we come across a function that requires more than one formula in order to obtain the given output. For example, in the toolkit functions, we introduce the absolute value function f of x, which is equal to the absolute value of x, with a domain of all real numbers and a range of values greater than or equal to 0. Absolute value can be defined as the magnitude or modulus of a real number value regardless of sign. It is the distance from 0 on the number line. All of these definitions require the output to be greater than or equal to 0. If we input 0 or a positive value, the output is the same as the input. F of x is equal to x if x is greater than or equal to 0. If we input a negative value, the output is the opposite of the input. So if f of x is equal to negative x if x is less than 0. Now, because this requires two different processes or pieces, the absolute value function is an example of a piecewise function. A piecewise function is a function in which more than one formula is used to define the output over the pieces of the domain. If you look at this figure here, this is what a function can be. It can be in pieces. We can create functions that behave differently based on the input x value. In this particular piecewise function, it's made up of three pieces. There's one piece, there's a second, and then there's the third. Now, we use piecewise functions to describe situations in which a rule or a relationship changes as the input value crosses certain boundaries. For example, we often encounter situations in business for which the cost per piece of a certain item is discounted once the number ordered exceeds a certain value. Tax brackets are another real-world example of piecewise functions. For example, consider a simple tax system in which incomes up to $10,000 are taxed at 10% and any additional income is taxed at 20%. The tax on a total income S would be 0.1 times S if S is less than or equal to $10,000, and $1,000 plus 0.2 times S minus the $10,000 if S is going to be greater than $10,000. So here's just an example of what a piecewise function is going to look like. When x is less than 2, it gives x squared. Now recall that x squared is a parabola. And what it's saying here is that at the value of 2, or when x is at 2. Okay, what it's saying here is that at the value of 2, it's saying that on the x squared parabola, everything is less than that 2. So you can see here that you have an open circle, and this graph is going everything towards the left on the x-axis. Now, when x is exactly 2, it gives 6. So what that means is, at this point, when x is exactly 2, it gives a point 6. So that is the only point that's highlighted there when x is exactly 2, which means that it is an inclusive point, but only when the y value is 6. And then what we have is when x is more than 2 and less than or equal to 6, it gives the line 10 minus x. So here's the line 10 minus x. And so at the value of 2, okay, it's saying that it is more than 2, but it's not including it. And then as the line is continued to be drawn, when it gets to the value of 6 on the x-axis, it's saying that it is less than or equal to 6, which gives you that particular dot. So again, a solid dot means that it's including, an open dot means that it's not including. So this is how we would write it. We would say f of x is equal to, now this is a piecewise function. On this graph, we have x squared if x is less than 2. So that is the purple. Then the green, okay, is that when we know that the output is 6, only when the input is 2. And then we know that we have the line 10 minus x, and that's if when x is greater than 2, so we have a circle, and it's less than or equal to 6, which means you have a dot here.